Okay, hello, good evening, or good afternoon, depending on which time zone you are in. And since we are talking about computing and at the heart of computing lie algorithms, so I will present to you an algorithmic problem and two solutions to it. After every solution, I shall run a fairly optimized implementation of the algorithm written in Rust, and we shall see how well the solution performs in real time. So this is a 10-minute talk and it has two demos. So let's begin. Okay, a graph. Okay, just a second. Sorry. Yeah. Uh, a graph is composed of nodes, edges, and edge weights. Of course, we know that. And we shall consider only simple graphs. So no self loops and parallel edges are allowed. And we shall assume that the edge weights are always positive integers for now, right? Now, the problem that we're trying to solve is to find the shortest path from the source S to a target T in the graph. Sounds simple, right? No, wait. Here's the real problem. We need to find the shortest path on the graph of New York City and San Francisco Bay Area, each of which has about 300,000 nodes and 800,000 edges each. And the reason I have underlined the word shortest there is because the paths are not necessarily the shortest, but they are actually they can be the quickest as well, depending on what edge weights you set. So if you set the edge weights to the time taken to travel between nodes, the paths you get are actually the quickest paths, right? So it's if the concept of shortest can actually be generalized. Okay, so going ahead, the classic solution to this problem is, of course, the Dijkstra's algorithm, and which appeared in the 1959 paper by Dijkstra called "A Note on Two Problems in Connection with Graphs." And no, that is not a typo. That is actually an archaic word in the title of the paper. And I'm glad that computer science has reached a milestone where we can find papers with archaic words in their titles. Anyway, let's move to the algorithm. So here is the graph that we had that we took as an example before. And we have added the source S to a frontier. And the green labels in every vertex represent the best known distance to that vertex from the source S. Next, we start relaxing edges. On each iteration, we take this shortest edge incident on the frontier and add the destination node of the edge to the frontier. Add the destination node of the vertex to the node to the frontier and update the labels on the nodes adjacent to the new frontier if needed. For example, in this node here at the top, the label was updated to 5 from infinity because we found the shortest path from S to that node via this node, which has a shortest path, which has a distance, which has a total distance of 5, right? And on the other hand, we did not update the label for 4 because the new path that we found to this vertex was actually longer than the earlier path we already knew, right? So we repeat this until the target T is found or we run out of nodes. And the complexity of this algorithm turns out to be order of V square, which is from Dijkstra's original paper. But over time, it has been improved. If you use Fibonacci heaps, the best known complexity is order of V log V plus E, right? And now, if you think, we can do slightly better than this, though. So if what happens if you search from both the source and the target in opposite directions, right? So you have one search that goes on, you start developing one frontier from the source and another from the target, and wherever both of those frontiers meet, you should be able to find a shortest path, right? And ideally, that should help us settle fewer nodes, and it should work well, right? Okay, so let's see how well it works. So here this is the implementation for Dijkstra's, and I'm going to run 100 queries, randomized queries. So we don't know from which edge to which, from which vertex to which vertex it is going to, the query is. But we see that on average, it takes about 13 milliseconds per query. And this is a graph that has 300,000 vertices and about 800,000 edges, right? And maybe if it could be a fluke because we just had 100 queries, right? So let's run that a couple of more times. And every time you see that the time, it roughly takes about 13 to 14, approximately 10 milliseconds per query, right? Okay, these are milliseconds, but I promised you microseconds. So we need to do something else. we need to do better than this, right? So in let's move to contraction hierarchies. In 2006, the Center for Discrete Maths and Theoretical Computer Science at Rutgers took up the shortest path problem as a challenge. Research groups were asked to submit papers, and out of it came a whole host of speed up techniques that could be used to make the shortest path computation faster. One such technique is called the highway hierarchies. Now, the idea is simple. The researchers posited that not all edges had the same importance in a road network. On one end, there were local edges that had low edge weights because the vertices were pretty close, and on the other end were highways with high edge weights because they connected nodes that were farther apart. Right? This way, the authors created subgraphs within the road graph. There was a subgraph for highways, and there was another one for local roads, and there were a few other ones for the categories of road networks present in the network. Fun fact, Germany categorizes their road into 7 categories. I have no idea why, but they do. So routing now under this model becomes like driving. To travel long distances, you want to hop on the highway as soon as possible and keep driving on the highway, only descending to the local roads when you reach close to your destination. And this is exactly how our search worked when using highway hierarchies, right? Now, an interesting variant of this approach is called contraction hierarchies, or CH, where every node is given a place in the hierarchy. Once we have this hierarchy of nodes defined, we can start applying the operation that gives CH its power, shortcuts. So, explain simply, if you have a shortest path from, if the shortest path, if U to V to W, for a vertex V, if U to V to W is the shortest path, then we add a shortcut from U to W. If you add this shortcut, any Dijkstra search that reaches the vertex U can bypass the vertex V altogether. This is called the contraction operation, right? Now, think about what we just did for a second. We added edges to the graph and we made it bigger in order to compute the shortest path faster, right? Now, going back to our example of what the running example that we have been taking. So the red numbers are actually the order, are the rank in which we are the ranks of the vertices or the orders in which we contract them. And if I run the contraction algorithm on this graph, I get that we have to add 2 shortcuts, one from 11 to 13 and another one from 12 to 13. After the shortcuts have been added, the search algorithm remains basically the same as bidirectional Dijkstra's, except for one small change. Our forward search will now only go from lower rank nodes to higher rank nodes, and the backward search will only go from higher rank nodes to lower rank nodes. For example, here, so if our search starts from a vertex 1, it will only reach vertices that are above the rank 1 in the forward search, and vice versa for the backward search. So the backward search only reaches the nodes that are actually higher than vertex 4 because I've, in this case, I reversed the direction of the edges, right? And there are a few considerations that we need to keep in mind when using this technique, which is that in what order should the vertices be contracted and how do you compute the importance? We typically do it using heuristics, but there are also optimal methods known, so we can use that. And okay, so this is a pretty simple technique. It's slightly hard to implement, but let's see how well it works. And I'll switch this again. And okay. Contracting, 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 and here. So we ran the bidirectional Dijkstras again, and we are just doing it for 10 shortest paths. So we got a latency of 9 milliseconds per query, whereas using contraction hierarchies, we are able to reduce it down to 43 microseconds. And the reason we are able to get this is because we have drastically reduced the search space for the bidirectional Dijkstras that runs in the query phase of the algorithm. Let's run it a couple of more times and see whether it actually remains static. So this is 100 queries, and we are getting again 13 milliseconds per query and 16 microseconds. And mind you, these are randomized queries, so I have no control over which shortest paths I'm actually running. And in all the cases, we are able to see about an order of magnitude of a speed up as compared to the bidirectional Dijkstra's, right? So yeah, well, that was the technique I wanted to discuss, and I hope you learned something about algorithm engineering today. Thank you.